Hi, my name is Tim and I'm here in Australia, and this is a humble toilet paper tube. Now we're going to model this as a surface and not worry about what happens through the thickness. But when I apply a force to this, one of two things can happen. The surface can bend, which mathematically corresponds to a change in the curvature tensor, or it can stretch, compress, or shear, which is really hard to do, and that would correspond to a change in the metric tensor. Now this dowel rod, in contrast, is thin in two directions. It's thin this way, and it's thin this way. So this we can model as a curve. Now it's very difficult to stretch this because it's made of wood, also to compress it, but it's very easy to bend it because it's so slender. But it does offer some resistance to bending. Now a chain offers no resistance to bending. It also offers no resistance to compression or shear, but it can be very strong in tension. So when you hang a chain between 2 points, you get a special curve called a catenary. Catenary comes from the Latin word catena, meaning chain. And because the chain can only support a tensile load, all of the links in the chain, their weight must be borne tangent to the curve in tension. So if you want to form an optimal shaped arch, what you do is you fuse the links in that position, and then you flip the arch or the chain upside down. And the resulting arch will be the optimal shape because all you've done is change the direction of gravity, and the weight of the arch will be borne all in compression. Now you may have heard that the Gateway Arch in St. Louis is in the shape of a catenary. Strictly speaking, this can't be right because the Gateway Arch is thinner in the center than it is towards the edges. So strictly speaking, it's not a catenary, but it's still very similar. And if you want to put a weight at the top of your arch, like if you want to put a monument up there, the first thing you do is you take the corresponding chain and apply the weight to that chain. The resulting shaped curve still bears all of the weight of the links in the chain plus the monument in tension. So if you fuse the links in this position and flip it upside down, you'll have an optimal shaped arch to have that monument either hang or sit atop the center of the arch. And if you add more weight, then the shape of the chain becomes almost piecewise linear. So next we're going to go through the mathematics that models this, but we wanted to start with the physics first.
For the sake of simplicity, let's assume that the solution is symmetric around x equals 0, that the highest point is at y equals h and the lowest point is y equals little h over a specified span. Let's let psi be the angle that a tangent vector makes with the horizontal. So psi is positive for positive x and negative for negative x. We also see that dx ds is the cosine of psi and dy ds is the sine of psi. Let's imagine a small piece of the curve of length delta s. That piece is held in place by a tension T that acts at both ends to balance the weight. The mass of the entire chain is m, its length is L, and g is the acceleration of gravity near the surface of the Earth. Balancing the forces gives the equation at the bottom of the slide. Dividing by delta S and taking the limit as delta S goes to 0 gives the following differential equations for T, the tension, psi, the angle, x and y in terms of the arc length S. If you've had a course in differential equations, or even a course in calculus, then you can solve for x, y, psi, and t. Although this is, in my opinion, the simplest approach, it is not the way that most people do it. So let's do things their way. In particular, one thing people like is to have a solution for y in terms of a hyperbolic cosine. Most authors take x to be the independent variable instead of s. So in this case, dy dx is the tangent of psi. Repeating the analysis above of a small piece of the curve gives the appropriate force balance. Dividing by delta x, as opposed to delta s like we did before, and taking the limit as delta x goes to 0 gives two differential equations that you see toward the bottom of the slide. Now let's step through the solution process. The first differential equation implies that t times cosine psi is a constant, which I'll call t naught. If you solve for t and plug that into the second differential equation, that gives you an equation for psi. That differential equation is separable, so it's easily solved. Nevertheless, many authors prefer an ordinary differential equation in terms of y, in which case the second derivative of y with respect to x is equal to a constant times the square root of 1 plus dy dx squared. This equation is usually solved by making a change of variable for dy dx, followed by a trig substitution that essentially brings us back to working with psi. So why bother? Integrating both sides and doing some algebra shows that dy dx is equal to the hyperbolic sine of a constant times x. The details are left to the interested viewer. Integrating with respect to x, again, gives us y. And if we write the solution in terms of little h, the height at the center of the chain, then we get a particularly nice form for the solution. That is, y is equal to little h times the hyperbolic cosine of x over h, provided that t naught is mgh over L. We can also solve for psi, since it's just the derivative of y with respect to x. Finally, we can solve for the tension, which reduces to mg times y over L. The graph shows the catenary colored by the tension. So note that the tension is smallest at the lowest point on the catenary and highest at the highest points. Thus far, we have assumed that the mass per unit length is a constant. However, we can easily relax that assumption. If we assume that the mass density ρ is an even function of x, then we can solve for y as shown. By manipulating the mass density, we can accommodate applied loads or varying thicknesses of the chain. If we apply a point load at the center of the chain, then we can solve for y as shown. Now this expression is a bit ugly, but it's essentially a constant plus a constant times a hyperbolic cosine minus another constant, so it's really not that bad. Now an upward point load, where F is negative, results essentially in two half catenaries, as does a downward point load, but in the limit as the load increases, the solution is almost piecewise linear. Here we see an animation with an upward force followed by a downward force. See how the curve is almost two lines at the end. Now again, if you want to construct an arch that supports a centered load, then you can apply that load to a chain so the weight is borne tangent to the curve. Then fuse the links and flip the chain over to form the optimal arch, where all of the weight is borne in compression. Again, varying thickness also changes the shape of the curve. In this case, the thickness of the red curve varies linearly with x, and it results in a shape that is different from the classical catenary, but not by much. And to finish, the Gateway Arch in St. Louis resembles an inverted catenary. If we flip it over and fit a catenary to it, then we have a decent fit. And fit a catenary to it, then we have a decent fit.